Now after discussing the limitations of the reversed Carnot, your cycle, refrigeration cycle, we will say that let us study the standard vapor compression refrigeration system. We already discussed what are the various limitations with the reversed Carnot refrigeration cycle. We can say that there is no use to use that your expansion, that adiabatic expansion by the help of turbine, because it is not economically feasible. And another limitation is the wet compression, that the compressor is dealing with your liquid and vapor mixture. So we will say that in the standard vapor compression refrigeration system, we can say to overcome the limitation of the reversed Carnot refrigeration cycle, we will replace the isothermal heat exchange process with the isobaric heat exchange process. That is, the heat rejection and heat addition will be at constant pressure, and instead of using the turbine for the adiabatic expansion, now we can use the isenthalpic expansion, that is with the help of a throttling device. So first of all, let us discuss what is the standard vapor compression refrigeration system. Suppose this is the line diagram of the standard vapor compression refrigeration system. This is your compressor. This is the compressor. So let us say the inlet of the compressor is 0.1 and outlet is your 0.2. After compressor, the refrigerant will go to the condenser. This is your condenser. In condenser, the process is from 2 to 3, let us say, and in this the heat exchange process is at constant pressure, not at constant temperature. Then we have a expansion device. This is a throttling valve. Instead of your turbine for the adiabatic, reversible adiabatic, or you can say isentropic expansion, we have isenthalpic expansion with the help of this throttling valve, and after this the refrigerant will go to the evaporator, in which heat addition, heat absorption process is there, and that too it is constant pressure heat absorption. So we can say that in the standard vapor compression refrigeration system we have 4 processes. Let us say the process 1 to 2. The process 1 to 2 is reversible adiabatic, or you can say isentropic compression. 1 to 2 is reversible adiabatic compression. 2 to 3 is reversible, this is also reversible isobaric heat rejection, reversible isobaric heat rejection. 3 to 4 is your isenthalpic expansion, and you very well aware of the fact that the isenthalpic expansion, or you can say in the throttling valve, the process is highly irreversible. We already discussed it in your thermodynamics that the flow through a throttling valve is your highly irreversible. So this process 3 to 4 is not a reversible process, this is a irreversible process. So I can write here it is a irreversible process. And then process 4 to 1 is this is again reversible isobaric, reversible isobaric heat absorption. The heat is absorbed from the storage device, or you can say the refrigerator, from the food items which we want to maintain at a temperature lower than that of surrounding, the heat is absorbed. So we can say in the compressor we have to do some work. So let us say the work consumed by the compressor is WC, heat rejected by the condenser is QR, and heat addition in the evaporator is QS. Let us say QS or QA, right? We will take it as QS. Generally this is heat supply. Now in the throttling valve, you know that in the throttling process there is no work done, right? You very well aware, if you remember your thermodynamics concept, then in the throttling valve there is no heat transfer and there is no work transfer. So in the isenthalpic expansion, we can say that there is no work transfer. No work transfer. Right. So we can say that this is the standard vapor compression refrigeration system. And if I plot this standard vapor compression refrigeration system on the TS diagram, let us put this standard compression refrigeration system on the TS diagram. Let us say this is TS, this is the vapor dome. In the standard vapor compression refrigeration system, and we can say if nothing is given in the question, if there is no mention about the initial state at the compressor, you have to always take the initial condition of the compressor to be at saturated vapor. Right, if nothing is mentioned, then we always take that the at the inlet of the compressor, the refrigerant is at saturated vapor phase. Right. Now from this we have an adiabatic compression like this. This is process 1 to 2. This is process 1 to 2. Always take the inlet condition of the compressor to be at saturated vapor. Let us say this is point 1, this is point 2. So this is adiabatic compression. Now we have constant pressure heat rejection, right? At point 2 the refrigerant is at superheated region, right? This is superheated region. So at point 2 the refrigerant is at superheated region. And we can say now, let us say here the pressure is PC, pressure corresponding to this condenser PC. So if I say that pressure in this condenser is PC and pressure in the evaporator is, let us say, PE. PE is the pressure in the evaporator which we have to maintain during the heat exchange process. So process 2 to 3 is constant pressure heat addition. So this is the constant pressure line. How to draw this? We know from our basic concept of the phase diagram. So this is the constant pressure heat addition. Oh sorry, heat rejection. This is the constant pressure heat rejection. Let us say this is point 3. In the standard vapor compression refrigeration system, you have to note two things. One is that the inlet condition of the compressor will be at saturated vapor. If I write, there are two things which you have to remember. Two conditions for the standard vapor compression refrigeration system is, first one is the inlet condition of compressor. Inlet condition of compressor is saturated vapor. It is saturated vapor. And second one is the outlet condition of this condenser. Outlet condition of this condenser is this saturated liquid. It is saturated liquid. You just remember this thing. We will design the system like this, that the inlet condition of the compressor is saturated vapor and the outlet condition of the condenser is saturated liquid. Now we have throttling expansion. So let us say this is the throttling expansion. Why we are showing it with the help of dotted lines? Because it is a highly irreversible process. So we know that irreversible process are shown with the help of dotted lines. right? So let us say this is 0.4, and now 4 to 1 is constant pressure heat addition. Constant pressure heat addition. Let us say this is constant pressure heat addition 4 to 1. So this is the TS diagram of standard vapor compression refrigeration system, or you can say the normal vapor compression refrigeration system will look like this. Inside the dome, you know that if the pressure is constant, then temperature is also constant. So these lines are the lines of your constant pressure. Let us say this line 2 to 3, this line is your PC is equal to constant. This line is PC is equal to constant, and let us say this line is PE is equal to constant. This line is pressure PE is equal to constant. This we have to maintain. And the temperature corresponding to this evaporator, let us say this temperature is TE, it is a lower temperature, and this temperature corresponding to this condenser is, let us say, TC. This outlet temperature is TC. So this is your TS diagram of standard vapor compression refrigeration system, right? Now these are the two conditions which you have to remember while drawing your standard vapor compression refrigeration system. Now we can say that if I compare this standard vapor compression refrigeration system with the help of Carnot refrigeration system, so we can say that in Carnot refrigeration system the heat addition process are isothermal. Here the process are your isobaric, and one process is irreversible. So if any one process is irreversible, then this whole cycle is irreversible. So you know that between the same temperature limits, the COP of a Carnot cycle will be maximum than this standard vapor compression refrigeration system. Now if you want to compare this standard vapor compression refrigeration system with the Carnot refrigeration system, we will discuss. If I draw the reversed Carnot refrigeration system in this diagram, then how it will look like, we will discuss it. So this is the standard vapor compression refrigeration system look like. So here you can say the work consumed by the compressor is, let us say, WC, work consumed. Here heat rejection is, let us say, QR, and let us say here heat supply is QS. Heat supply is QS. There is no work and no heat transfer associated with the throttling process. So this is the case. Now somehow some students will have a doubt in their mind. We will discuss it here itself, that when we discuss the reversed Brayton cycle in the gas refrigeration system, we discussed the reversed Brayton cycle. In that reversed Brayton cycle, we have these three processes similar: constant pressure heat exchange and reversible adiabatic compression. But in gas refrigeration system, we use turbine, or you can say the reversible adiabatic expansion, rather than this throttling process. Now in the interview, if you face some interview of the PSUs, or some concept will be must for you to understand why we are not using the throttling device in reversed Brayton cycle. Why we are not using it? Why we use turbine there? Now if you remember your discussion of the thermodynamic relation chapter in the thermodynamics, the last chapter which we discussed, there is a term known as Joule-Thomson coefficient, right? Joule-Thomson coefficient is associated with the throttling process, you remember it. Now if you go through that concept, you know that you know that the Joule-Thomson coefficient for the ideal gas is 0, right? You know that the Joule-Thomson coefficient for the ideal gas is 0. We already discussed it. Now, what is this Joule-Thomson coefficient? The Joule-Thomson coefficient formula is dT by dP at constant enthalpy. At constant enthalpy. So for the ideal gas, this Joule-Thomson coefficient is 0. That means there is, during the throttling process, there should not be any change in the temperature. Temperature is not changing, right? Now, if you remember that in the gas refrigeration system, the most common refrigerant which we are using is air. And in that case, you know that air can be treated as an ideal gas. Air can be treated as an ideal gas. So if you use the throttling device in the reversed Brayton cycle, what will be the thing if we say that if you use the throttling device, then expansion is there, pressure will reduce, but because air is an ideal gas, and for the ideal gas the Joule-Thomson coefficient is 0, the Joule-Thomson coefficient is 0, that means temperature will remain constant. Temperature is constant. Temperature is constant during throttling. Right, this is the meaning. Temperature is constant during throttling. dT is 0, or so temperature will be remain constant. It means if you use that throttling device in the reversed Brayton cycle, when the refrigerant is throttled from condenser temperature to the evaporator temperature, the thing is that the temperature will not change. The temperature will not change. Temperature will be the condenser temperature. Suppose if you say that, let us discuss about the reversed Brayton cycle. Let us say that the condenser temperature is suppose 30 degrees Celsius. The evaporator temperature is, let us say, minus 10 degrees Celsius. This we want. But if you use the throttling device in that reversed Brayton cycle, at the end of the expansion or at the end of the throttling process, the temperature at the inlet of the evaporator will be 30 degrees Celsius. It will not change. It will not change. And now we have to take heat from the evaporator. Suppose you just make one thing clear, that suppose if you say that the evaporator temperature is minus 10 degrees Celsius, then let us say that the food which you want to cool down, which you want to maintain at a temperature lower than that surrounding, suppose this food is at, let us say, suppose 20 degrees Celsius. So because of this temperature difference, minus 10 to 20 degrees Celsius, the heat is transferring from food to the evaporator. This heat, what is this heat? From where this heat is coming? This is coming from the food which is present in the refrigerator or some item which you want to cool down. So this temperature of this food will be greater than the temperature of the evaporator or temperature of the refrigerant which is flowing in this evaporator. Then only heat is going from this food to this evaporator, right? Then only, because heat is flowing from higher temperature to the lower temperature, then only this heat will be supplied to this refrigerant. So this temperature must be greater than the temperature of the evaporator or temperature of the refrigerant in the evaporator. But if this temperature is not decreasing, the condenser temperature is not decreasing, so now the temperature is 30 degrees Celsius. The temperature is 30 degrees Celsius. Food temperature is 20 degrees Celsius. Now heat is transferring from 30 to 20. Food will become more, food will be at more temperature now, right? You cannot extract heat 20 from food to evaporator now. Now you cannot extract heat from this food. Right, now heat has a tendency to flow from high temperature to the lower temperature. That's why we are not using the throttling device in the reversed Brayton cycle. That's why we are not using, because it is working on the air and it is acting as a ideal gas, and for the ideal gas during throttling there is no change of temperature. But we want that during the expansion from condenser pressure to evaporator pressure, during that expansion there must be change or there must be decrease of the temperature. Then only we will be able to extract the heat from the food. Otherwise it is not possible. That's why we are not using, and we already discussed that why we are not using adiabatic expansion in this reversed Rankine cycle, or you can say in this standard vapor compression refrigeration system, because it is dealing with the liquid phase and the specific volume of the liquid is very less, and we can say if it is very less, then there should not be so much work which can be compensated, and it is not economically feasible, right? So these are the reasons. They may ask you in different interviews, so you will be able to answer those things.